Okay, so in the last class, we have just introduced what is meant by integration, the integration over a single variable. So today we are going to introduce line integration. So the line integration, the motivation, we can say that the finding work done, find the work done by a force. So the work done or infinitesimal work done, we can say that it is the product of the force and displacement, or it is a dot product between the force and displacement. So if F is a force applied, so if F is a force applied and dl is the displacement, then the work is defined like this: dw is equal to F dot dl. Then what would be the total work? So what is the work over a distance? Suppose the particle, some particle we have, maybe a car, and somebody is pushing on it, and it moves from one point to the other point. Okay, suppose it starts from A and reaches the point B. So every time it exerts some force and it moves from A to B. Then what is the total work? So total work we can find by integrating F dot dl throughout this line. Okay, so here I have to integrate F dot dl through this line, through this curve. So such kind of integration is called line integration or line integral. Okay. Then what would be the area integration or surface integration? So surface integration, usually the motivation can be finding flux of liquid flow. Okay, so the situation is like this: some liquid is flowing in the region. Okay, and we have some area, the cross sectional area, and I just want to know how much liquid is flowing through this area per unit time. Okay, now this can be found out. So if you have a very finite area, a finite area vector I am denoting as ds, and the velocity vector of this liquid flow I am denoting as v, then the flux through this small area is denoted as v dot ds. Okay, so these are flux simply through this small area. Now how we can find the flux through the total area? So that we can integrate we have to integrate this infinitesimal flux throughout in this entire shaded region. So the total flux would be integral of v dot ds through the surface of the shaded region. Okay, so what I will do is we'll have very large number of infinitesimal areas, and we have to add the flux through each infinitesimal area. That will give the integral v dot ds. So such kind of integration is called surface integration. Okay, so we have discussed the line integration. So in line integration, we are adding the vector through the line. Okay, so what I will do is, so suppose if you want to integrate from A to B, so the A to B can be divided into a very large number of small segments. So each segment has length dl. So we can find f dot dl for each segment and add it. So that is integral f dot dl. Okay, that is what is called line integration. That is, you are integrating over a line, over a curve. Okay, and in case of surface integration, so we are going to integrate our area. So first we will find out the product between the vector and the surface area, the infinitesimal surface area, and we'll find the sum of such product for all areas. That will give the surface integration. Next is the volume integration. Now, what is the motivation behind this volume integration? So, motivation can be to find the total charge in a charge distribution. So, this is only one example, so there can be many other examples as well. Suppose you have some chart distribution. Okay. Now this chart distribution has the varying chart density. Okay, the chart density is not uniform. So varying chart density with position. Okay, so we have some variable chart density. So suppose I am denoting as rho as the chart density. So rho of XYZ. So the when location changes at different locations, we have a different chart densities. Okay. Now what would be the charge in a very small area, or sorry, in a very small volume? So you can consider an infinitesimal volume d tau. The charge amount of charge in that infinitesimal volume we can denote as rho times d tau. Then how we can find total charge? So this entire charge can be viewed as the sum of very large number of infinitesimal volume. So the total charge Q is integral rho d tau over the volume. So we are integrating over the volume here. So this kind of integration is called volume integration. So this is only one of the example. So there are many other example, like you can find the total mass integration. So suppose any quantity which is having volume distributions, then we can find this total quantity by volume integration. So these are the three types of integration. So we'll discuss each of these things in detail in the next sessions. Thank you.